So let's continue in 6C using the information we discussed earlier to help us get through this particular example on detecting counterfeit coins. So here's the situation. Vending machines can be adjusted to reject coins above and below certain weights. There's a tolerance value there. The weights of legal U.S. quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? I know this seems like a lot of information, a lot of numbers, a lot of decimals, but if we take what's given to us and put it on a picture, on a diagram of a normal distribution, it should make more sense. So I would always start off with a problem of this nature by showing and drawing my mean on a diagram. So here I have a normal distribution. I'm just going to draw a line there at the peak because that always represents your mean right there in the middle, and in this case it is 5.67. So I know that much, and it says my standard deviation is 0.07 grams. Remember with the normal distribution, we go up and down one standard deviation, up and down two standard deviations, and up and down three standard deviations. So we can use the 68, 95, 99, 7 rule. So if 5.67 is in the middle, and one standard deviation equals 0.07 grams, then to get to one standard deviation above the mean, I would just add 0.07 to 5.67. To get to the next value up, I would add 0.07 to that value. I would keep adding 0.07, or going to the left, subtracting 0.07 to determine those data values on the x-axis. It's important to know where those data values are. So determine the values on your x-axis. Okay, so your values should match my values on my x-axis with respect to the weights of quarters. The mean is in the middle, and I marked values for one standard deviation up, two standard deviations up, and three standard deviations above the mean. Same thing, 1, 2, and 3 standard deviations below the mean. You just either add 0.07 or you subtract 0.07. Now that I have these x values, I can draw a picture with respect to what area am I talking about on this curve. So I want to reject quarters that are more than, so I want to reject if it's greater than 5.81 grams, and if it's also less than 5.53 grams. Well, you should see those two exact values on your x-axis. So now let's draw some lines and do some shading. So I'll just incorporate a different color here. Maybe I'll go with this bright blue, and I'll mark a bright blue line at 5.53, and a blue line at 5.81. And it's stating that I want to reject quarters that are greater than 581. So that's all this area to the right. Greater than means to the right. Less than 553, so I find 553 and I shade everything to the left. And those shaded blue portions that you see on this graph represent the area that we want to reject. We want to reject any quarters that lie in those two regions. Once you've got the picture, then it's just a matter of figuring out what those little percentages are and adding them up. So if we go back to our previous page, and actually I'm going to want to change a number here, change the color anyway, we saw some values for each strip. These little tiny tails was 0.15%. The part up there, as you can see on this diagram, that light green part was 2.35%. And so on. We had a 13.5% and a 34%. All those percentages on this right-hand side added up to 0.5 or 50%. So let's see what the strips are that I have shaded on the quarters graph. Well, according to what we just did, this little tail on the right is 0.15%, and that part right above it was, I think, 2.35. Right, that was 2.35%. So those two strips correspond to those two values of area that we had found earlier. So that one's 0.15 and this one was 2.35. And remember, everything is symmetric. So the blue part, that light blue part shaded, is the part that I want to reject. Those are the quarters I want to reject. So what percentage of quarters will I be rejecting? Well, 0.15 plus 2.35 gives us 2.5. So for greater than 5.81, that's a total of 2.35 plus 0.15, which is 2.5%. So I'm rejecting that amount on the right. And on the left, it's the exact same thing because of the way this problem is stated. On the left side, I would be rejecting 2.5%. So if I add those together, I would actually be rejecting 5% of the quarters that would come into that machine. So based on this tolerance, I'm going to accept any quarter that's between 553 and 581, but I'm going to reject all the quarters outside of that. So important, and I can't emphasize it enough, to draw a picture. Always, always, always draw a picture. All right, let's see what the second part of this problem states. Okay, so you're sitting there, you've got a bag of 500 quarters, and you're going to start feeding those into the machine. How many of those quarters will be rejected based on the result we found above? Well, we found above that 5% would be rejected. So if I have a bag of 500 quarters, that means 5% of 500 would be rejected. And that's going to be what amount? So we'd be looking at a total of 25 quarters would be rejected. Okay. So now let's take this one step further. Suppose the machine is set to accept all the quarters that lie within 3 standard deviations of the mean. How many would be rejected then? Well, if I'm looking at 3 standard deviations of the mean, if we go back to the 68, 95, 99, 7, I know that 99, let's get back here. I know that 99.7% of the data falls within 3 standard deviations of the mean. So that means if I'm going to accept the coins that fall within 3 standard deviations of the mean, that means I'm going to accept 99.7. I'll accept 99.7%. What percentage will I reject? Well, it's going to be 0.3%. So I'll accept 99.7. I'll reject 3%. What does that equate to in terms of quarters? Well, if I have 500 quarters, 99.7 99% of 500 and then 0.3% of 500 will answer those two questions. Find your values. So 99.7% of 500 quarters would be 498.5 quarters, but I just rounded that to 498. We don't have a half a quarter. And 0.3% of 500 quarters would give me 1.5 quarters. I raised that up to 2. The reason I didn't leave it at 1 is because my 498 plus my 2 has to be my total of 500. So that's using the 68, 99, 95, 99.5 rule with the normal distribution. Okay, let's do one more example. We've got an exam that was taken by 1,000 students. The scores are normally distributed. We've got a mean of 75 and a standard deviation of 7. I've given you a graph to kind of help you orient yourself with this problem. And I want to answer the following questions. How many students scored above 82? What does that 68, 95, 99, 7 rule tell us about that? And I also want to know how many students scored below 61. What does the rule tell us about that? Okay, so set up your x-axis, what values you're going to have on your diagram along your x-axis. That's going to help you set the stage for determining your percentages. So do that and then we'll compare. All right, so let's answer the questions. I want to know how many students scored above 82. The mean of 75 is at the middle mark. I went up 3 standard deviations to give me data values on my x-axis of 82, 89, and 96. I went below 3 standard deviations one at a time, giving me data values on the left of 75 to be 68, then 61, then 54. So if I want to know how many students scored above 82, then I'm going to find 82 on that axis, and I'm going to shade everything to the right or above 82. I got a couple of ways I could look at this. Everything above 82 is from that blue vertical line at 82 to the right. And I know that half of this figure has to be 50%. I also know that this dark green strip is half of 68, which is 34. So if I take 50% of the data and subtract this 34% strip, that'll tell me what's left to the right of 82, how much area is left. That gives me 16% is shaded green, and I have 1,000 students, so 16% of 1,000 students would be 160 students. So 160 students scored above 82. That's 160 out of the 1,000. All right, next question. How many students scored below 61? So if I go to my table, go to my diagram, find 61, and shade to the left because it asks for less than 61, I shade everything from 61 to the left. I don't stop, I keep going, I shade the entire graph below 61. And I want to know what percentage that is. A couple of ways I could figure it out. Based on the little strips we discussed earlier, I could take 0.15 and add that to 2.35, and that would give me 2.5%. So that's one way I could figure it out. Or I know the whole left side is 50. So if I take 50% and subtract from it half of 95, because 95 is everything from the middle to that 61. That's area. 50% minus half of that 95 would give me 2.5% as well. So you can find the 2.5 either way. It's whatever way makes the best sense to you. or makes the most sense. So if 2.5% of the students scored below 61, 2.5% of the 1,000 students would be 25 students that scored below 61. I know that we did this earlier, but just to emphasize how easy it is to determine the percentage for each of these strips. Remember, we go out 3 standard deviations in each direction, and that represents a strip of area under the curve. And so this strip between the mean and 1 standard deviation can be found by taking half of 68%. So this strip we found earlier was 34%. This next strip between 1 and 2 standard deviations can be found by taking half of 95%, because 95 is the whole thing from left to right, taking half of that just looking at the right-hand side, half of that in, and then subtracting the 34% away from it. So this strip is 13.5%. All right, this next strip, which represents from the 2nd standard deviation, or 2 standard deviations to 3 standard deviations, this little small amount is calculated by taking 99.7, cutting it in half, and then taking away from that the 34 and the 13.5%. That gives us a strip that's worth 2.35% of area. Okay, and then finally, to do the tiny tail, the amount of area that's below that curve on the farthest right, that's beyond the 3 standard deviation mark, I take 50% and subtract from it half of the 99.7, because half of the 99.7 goes all the way to the 3rd standard deviation mark. And I just want the little leftover that's beyond that. So 50 minus half of that value is 0.15%. That tells you the percentage of your data that lies in each of those strips. Again, that's helpful when you're using the 68, 95, 99.7 rule. Okay, I will stop this video here and I will finish it up with a part 3.